Good day, everyone. I'm Desmond Yeoh here at Matric Number 2110924993, a final year electrical engineering student at Universiti Malaysia, Perlis. And today, I present to you a breakthrough in system in real-time AI vision, OpenCV-based image prediction with location identification using Python. The mission is to eliminate human limitations in object detection tasks, from fatigue to inconsistency, using a low-cost, high-efficiency AI system that predicts objects and their precise spatial locations in real time. The main objectives are to develop a computer vision AI system using Python programming language, to design an OpenCV-based image prediction with location identification using Python, and to evaluate the overall system performance. This is a pure software-based system. The project was built using advanced modeling, algorithm training, and also performance evaluation. So the core tools include Python, OpenCV, Yeoh, RoboFlow, and Google Colab. So for the tool description and justification, so the AI pipeline is built on robust and industry-proven technologies. The Kaggle is used for high-quality image datasets. RoboFlow is used for annotation, pre-processing, and augmentation of the resistor datasets sourced from Kaggle. Yeoh by Ultralytics is used for ultra-fast object detection. Google Colab with Google Computers and NVIDIA T4 GPUs is used for cost-efficient and GPU-accelerated AI model training. And Python and PyCharm is used for rapid and scalable development, and as well as OpenCV is used for real-time image processing and video frame annotations. So why this step, you might ask? Because it gives real-time inference, high detection accuracies, and cost efficiency, all just from the standard PC webcam and no exotic hardware.
Now, for the demonstration of tool application, let me walk you through how it all comes together. First, we start by collecting image data from Kaggle. Why Kaggle? Kaggle is a professional software website which allows users to share and open source high-quality image data as well as train AI models for public use. Here, we can observe a resistor image dataset of high quality taken with a USD microscope. Over here, we can see the usability of this dataset, which is rated by Kaggle based on several criteria. To use this dataset, we will first need to download it by clicking the download button here. Now, before we can train our AI model to be able to detect custom objects, we will first need to annotate and label the images, pre-process them, and augment them. This can be done by using RoboFlow. It is a professional image data annotating, pre-processing, and augmentation software for computer vision. First, we will upload the sample image data of the resistors onto the software. Next, we will need to manually annotate the bounding boxes and label the image of which part or region of the image is a resistor. When it is done, the dataset should look like this. Next, we apply pre-processing and augmentation techniques such as orient, resize, grayscale, flipping, rotation, and brightness variations, and split the image data between training, validation, and testing for the AI model. The best ratio to split the image dataset is 88% for training, 8% for validation, and 4% for testing. When it is done, it should look like this. Once it is done, we can download this dataset. Show the download code, and copy the code generated. Now, we can use this annotated dataset to train our Yeoh V11 AI model with Google Colab. So this over here, we have the Google Colab environment. First, we need to install and import some important libraries like Supervision and also Ultralytics for the Yeoh model. Next, from the code generated before, we paste the code into Google Colab and run it to import the annotated image dataset from RoboFlow. Now, we are able to train our Yeoh model. For this project, I've trained my Yeoh model for 200 epochs. Ideally, you want to train it for at least 100 epochs to achieve desirable results. Here, we can run a few scripts to generate the performance metrics of the training results. After that, we can use this line of code to validate the Yeoh model, and then test the Yeoh model to predict on new sample images of resistors which was never used in training or validation. Here are the results for the prediction. As we can see, the Yeoh model is able to detect resistors accurately and consistently. Next, we can export the trained Yeoh model for deployment in the form of a .pt file. Now to deployment. Using Python and OpenCV library in PyCharm, this is the Python script for the program that I've developed and designed, which is needed to run real-time object prediction and location identification system. First, we import the necessary libraries. This is the class function that handles real-time object detection with distance estimation. This is the class function to load the YOLO model from the path to the .pt file. This function allows the YOLO model to perform object detection on a frame. The calculate distance function works to calculate distance on an object using camera geometry based on the triangle similarity theorem. This is the plot boxes function. It is used to process the detection results and annotate the frame with bounding boxes and labels of the detected object. And lastly, this is the main function to run the object detection pipeline using the OpenCV library. Now let's run the program to have a look at the results. As you can see, the system captures live webcam video, detects objects, and draws bounding boxes, labels them, and calculates the XY location. And here's the best part, it estimates the depth and distance using the triangle similarity theorem. As you can see, I am currently seated approximately 47 centimeters away from the camera. So this code dynamically loads the YOLO weights and uses GPU acceleration via PyTorch and continuously predicts and annotates live frames. This is a real-time high frame per second AI model running in my laptop environment.
So the model's performance was validated under multiple real-world constraints. So first up, we have the system's accuracy. So the model's performance was validated under multiple real-world constraints. So first, we have the model training performance metrics results. So the graph above shows the performance metrics as a result of the YOLO AI model training for 200 epochs. So the confusion matrix below shows the performance of the classification model across 4 classes: face, hands, resistor, and background. So the diagonal elements indicate the true positives, while the off-diagonal elements indicate the false positives. So as you can see, the losses decrease gradually with more model training epochs, and the mean average precision increases gradually with more training epochs, and the model is reliable in classifying with more true positives than false positives. Next, we have the accuracy of the system. So the detection accuracy of the system is tested by using a series of images containing resistor quantities ranging from 1 to 16 to see the amount of resistors that it can detect by the system under controlled lighting. So we can see that there's 100% accuracy achieved consistently from 1 to 6 resistors, and as the resistor increased beyond 6, there is a drop in accuracy, with 80% being the lowest accuracy recorded. So this might be due to scene complexity as more objects overlap. So next, we have the system consistency. So the consistency of the system is tested by running a single image of 5 resistors for 30 consecutive iterations under ideal conditions. So the confidence level of each detected resistor is measured, and the flat horizontal line indicates high consistency in the model prediction for confidence for all detected resistors. So from the graph, we can see it is highly consistent based on the flat horizontal line trend, and the high confidence levels with 0.95 or 95% being the highest and 85% confidence being the lowest. So it's very highly deterministic and reliable model performance. Next, we have the reliability of the system in different illumination intensity. So the system's reliability is tested under different ambient lighting conditions ranging from complete darkness at 0% to full brightness at 100%. So it shows that the model is highly consistent in detecting results in moderate lighting levels around 25 to 75%. So there is a reduction in the detection accuracy in underexposed and overexposed brightness conditions. So this is due to the partial loss in the feature visibility and the pixel contrast, and also the weak gradients that detect the object boundaries clearly. Next, we have the reliability in different ambient color backgrounds. So the system is tested across multiple ambient background colors to observe changes in detection accuracy. So the system is able to perform perfectly on neutral tone backgrounds such as white, black, and gray. So the system completely fails in the presence of high saturation background colors such as red, green, and blue. So this is due to the color similarity with the background and also not enough dataset diversity. Lastly, we have the distance detection accuracy. So the system's location identification feature is tested to evaluate the system's ability to estimate spatial distance between the camera and the target objects using monocular camera setup. So as you can see, there is a high accuracy in low to medium range around 10 to 30 cm away from the camera. So the accuracy significantly drops and fails completely beyond 60 centimeters in the high range. So this might be due to the limited resolution of the camera and the loss of depth sensitive features to detect small objects at greater distances. However, when compared this system to an older RCNN-based model or traditional methods, YOLO-based implementation significantly reduces latency while maintaining detection integrity. Next, for the tool limitations. Like any other engineering tool, this system has its constraints. So first is the Google Colab environment limitation. So Google Colab being cloud-based, the model sessions are not saved. Every time the tab is closed, we must rerun training cells unless Jupyter Notebook is used locally. Next, we have the webcam resolution constraint. So a standard 720p webcam cannot detect small objects beyond 60 centimeters as the performance drops sharply at that range. Also, it is a monocular system setup, so there is no 3D spatial mapping. So future improvements may include stereo vision, LiDAR integration, or even transformer-based vision models. To conclude, this system proves how modern tools like YOLO, OpenCV, and Python, when combined thoughtfully, can solve complex real-time computer vision challenges with low cost and high precision. What I learned is the strength of YOLO and OpenCV lies in their ability to operate on constrained hardware, but their limitations must also be acknowledged in high variability conditions. So this is only the beginning. Imagine integrating this with robotics, drones, and also embedded surveillance. So this is the future of visual intelligence. Thank you.